about now.
There we go.
Business now.
Yeah.
So yeah, this is a subject that you know, it's not part of my original science background in malacology or the study of mollusks. I come more from a taxonomy field, but this is something that it really raised my interest in the past few years, especially now that it's becoming better understood thanks to you know, a big cadre of scientific papers being published and lots of scientific research being done on the subject, and the fact that it has raised the interest from, you know, many stakeholders in conservation and shell fisheries and the industry in general. So we started really getting interested, the museum itself getting interested in mollusk conservation with the organization in 2016 of the Mollusks in Peril Forum, when we really became acquainted with this kind of research with the topic of ocean acidification. And some of the most prominent scientists working in the field of mollusks and ocean acidification. That's a picture of the group back then. And, you know, we've been speaking with Sam and really considering doing something similar, probably using the Zoom resource, or maybe even live. So keep your eyes peeled for that. It may be coming soon. Anyway, why mollusks? Well, mollusks are an important group in terms of global biodiversity, with more than 80,000 named species, and many more yet to be discovered, as some of you know. There are also important links in the ocean food webs and terrestrial food webs, but here we'll be talking more about seawater in the ocean. And last but not least, very important as a food staple throughout many cultures in our planet. So there's also the human link. So yes, we do worry about mollusks, and we do worry about those changes that are happening and their effects on mollusks. So today we'll cover a few topics, and I don't have a lot of slides, but those topics are, you know, some of them are a little bit convoluted. So I want to make sure that when you leave here today, you have a very good grasp of some of the topics, such as the relationship between, you know, the atmospheric carbon dioxide in the oceans. What is ocean acidification? How mollusks make shells, and how they need something called carbonates to make their shells. And then what happens to shells in a situation of ocean acidification. And then to look at that, we'll look at three different scenarios. The open water species that we call holoplanktonic, such as pteropods, sea butterflies, you know, is the name that they're better known with. The effects on larval shells, the effects on adult shells, and then some closing thoughts at the end. So let's see what we have to say here. So let's talk a little about the relationship between carbon dioxide in the atmosphere and the oceans. So since the beginning of the Industrial Revolution, which was about the last half of the 19th century, the concentration of carbon dioxide has increased a lot in the atmosphere due to human actions, human activities, such as most of all burning of fossil fuels and other things as we'll see next. So as a result of this intake of carbon dioxide coming from the atmosphere into the ocean, the pH of surface ocean waters has fallen by about 0.1 pH units. And when you look at that, it says, well, 0.1 pH unit, that's not a lot. The problem is that pH units are based on a scale that's called a log scale, logarithmic scale. So the change in 0.1% represents basically 30% increase in acidity in ocean waters, resulting from that little 0.1 increase in pH units in the 20 plus years since the beginning of the Industrial Revolution. So that's important going forward in this talk. So the more this carbon dioxide is released into the atmosphere, the more it is absorbed by the ocean, and the result will be ocean acidification. So let's see a little more on atmosphere and ocean when it relates to carbon dioxide. So again, it's kind of repeated here, but what I'm trying to impress on you is the fact that the more carbon dioxide we have in the atmosphere, the more it will seep into the ocean. Some of the main reasons for that is the burning of fossil fuels, such as car emissions, basically means of transportation using fossil fuels. And also a very important one is the destruction of forests. Forests absorb a huge amount of carbon dioxide. And when the forests are gone, that carbon dioxide doesn't go anywhere and ends up in the ocean. So when carbon dioxide is absorbed by seawater, there will be a little game there. There will be a series of small chemical reactions that will happen to that molecule of one carbon to oxygen, CO2. The configuration will change a little bit, and it's a very, very delicate balance that happens there. So one of the things that happens, as I'll try to show you next, is there will be a huge increase in the concentration of free hydrogen in seawater as CO2 is entering the oceans. So as you see next, the whole process has far-reaching implications for the ocean environment and all the creatures that live there. So what happens to carbon dioxide once it enters the water? Basically, it will shift the equilibrium or the balance. Just a fancy word for balance, equilibrium. Will shift between bicarbonate, carbonate, and carbonic acid. Now, don't be impressed by the molecules. Just remember the formula. The good guy here is carbonate. Carbonate is one of the main components of shells. It's like the 1/2, quote unquote, of the calcium carbonate couple, quote unquote. That is the main component of shells. So I want to impress that idea also on you, that shells, the basic component of shells is called calcium carbonate, and it's basically a molecule of, an atom of calcium and 2 of CO3. So let's look here at something that's, I was trying to find a way of explaining this basic balance of carbon dioxide in the ocean, and I found this little cartoon here that's divided into 2 parts. The first one is an ideal situation, pre-industrial revolution, late 1800s. The ocean acidification as we know it today had not started yet back then. Okay, let's look at what happens. And it does happen. Carbon dioxide is absorbed by the ocean in relatively small amounts under normal, quote unquote, conditions. As that carbon dioxide enters the water, there's formation of carbonic acid and release of free hydrogen. So that free hydrogen is key to the process. That free hydrogen, what does that free hydrogen ions or charged atoms will do? Well, they will sequester carbonate ions. If there is a little amount of carbon dioxide entering the ocean, the amount of hydrogen ions is relatively small, and there's a lot of carbonate ions left behind, and that is that other half of the shell component of calcium carbonate. Okay, so under normal circumstances, basically what happens is there's a lot of carbonate ions, carbonate free, for the manufacture of abundant coral reefs, mollusks, and other marine calcifiers or other marine organisms that have shells made of calcium carbonate. So there's a little that's sequestered by the free hydrogen ions to make bicarbonate, but there is still a lot left. Now, let's look at the other half of that little cartoon here on the right. So this is a projected situation for year 2100. Far ahead, but not too. I mean, 79 years into the future. So we will have higher concentration of CO2, carbon dioxide in the atmosphere as a result of the burning of fossil fuels, deforestation, and minor other things that are happening in that direction. So there will be more carbonic acid being formed because there's more carbon dioxide. So the acidity tends to increase with the release of free hydrogen ions. There will be more free hydrogen ions. And what happens then is that because a lot of those free hydrogen ions are sequestering, are reacting with carbonate, there will be fewer carbonate ions, and a lot of bicarbonate will be formed. So the take-home message here is that with fewer carbonate ions, there will be less chance for shell formation or the formation of skeletons in marine organisms that use calcium carbonate for that purpose. I hope that's clear now. If you have questions, again, feel free to write in the chat and I'll try to address them at the end. Now, look here on the little graphs, the pre-industrial revolution and the projection for 2100 showing the pH of seawater. The pH of seawater currently is 8.1 in average, global pH, average of the global surface seawater in the oceans. And the projected pH is much, much, much lower than that. Remember that, and I'll explain pH next, the decrease or the change in one pH unit means a concentration increase or decrease of tenfold. So that's basically the definition of a logarithmic change, a logarithmic scale. So let's talk a little about pH. So this drawing explains in real life terms the concentration of free hydrogen, or the pH, of several substances. So to the right here, we have less hydrogen, free hydrogen in a medium, or such as seawater or other media. So we have a higher pH. So the pH would be the exponent here. pH 14, very basic. Household bleach has a pH of 12, which is very, very alkaline. Also not good. You don't want to go too far in either direction. So, conversely, the more acidic substances have a smaller pH, a lower pH, and good examples are, for instance, an acidic fruit such as tomato juice that has a pH of 4. I think Coca-Cola ranges in the same ballpark. Our gastric juices have a pH of 2 thanks to the presence of hydrochloric acid. And that's one of the reasons why digestion happens, right? We have that breakdown of things there in your stomach thanks to those gastric juices. Over the past 15 million years, and we'll talk more about that at the very end when we make the prognostics and what's may happen into the future. But over the last 15 million years, the geological record has shown that the oceans have had a pH consistent with 8.2. And over the past 200 years, the ocean pH had dropped down to about 8.1, which represents a 30% increase in acidity over those past 2 centuries, over those past 200 years. So just keep that in mind going forward here. Okay, this here is a classic. I first saw this picture when I was in graduate school way back in 1985. And it was cut a little shorter here, but it was already, being taught at graduate school level, and everyone was already, pulling their hairs over what was happening. This is basically the history of the presence of atmospheric carbon dioxide concentrations directly measured at Mauna Loa in the Big Island, Hawaii, since 1958. So it begins here around 1958 and ending about 2008. The red line here, the red curve shows the atmospheric carbon dioxide. In blue, the concentration of ocean carbon dioxide. And you can see that as one increases, the other one follows suit. And in green, the pH. So this curve is known as the killing curve, named after the scientist who first came up with that those three curves. And it's a classic piece of evidence on the man-made increases in greenhouse gases, and also mainly presence of carbon dioxide, which in the atmosphere is one of the greenhouse gases. That's another story that are believed to cause global warming. So those records are exclusive for Mauna Loa, but the measurements have been independently confirmed at many other sites around the world. So this in this graph again, a 0.1 change in seawater pH. It's about 30% change in the concentration of carbon dioxide. This is the same curve today, and it's just between just the curve for the presence of carbon dioxide in the atmosphere up to year 2020. So things didn't get any better since 2008, which is the end of the other curve. So there's an annual fluctuation here that's a detail between any given year between January and October, showing some fluctuation. And that's because there's more uptake of carbon dioxide by trees in forests during the summer in the northern hemisphere. There's more plant activity in the northern hemisphere than in the southern hemisphere, and that shows the difference. A slight decrease in the presence of carbon dioxide, and then it goes back, cycles back in the winter, and so on. So what I'm trying to show you here is that the presence of carbon dioxide in the atmosphere keeps increasing. And here you have the units in parts per million of carbon dioxide in the air. I'm sorry. So I hope I gave you a good introduction to ocean acidification and the relationship of atmospheric carbon dioxide and the oceanic carbon dioxide.
That the carbon dioxide in the air would change the acidity of the ocean water.
I will ask you to please kindly mute your computer or telephone and write the questions in the chat manner, in the chat format. Thank you. So again, I just want to show you a simple image that kind of summarizes all the previous slides on that. Is that the more carbon dioxide we have in the atmosphere, the more carbon dioxide we have in the ocean, and the less carbonate is there for shell making. That's where the beginning to make the connection here with mollusks. Now I want to talk a little following our menu there that I presented to you in the beginning. I want to talk a little about shell making. Some of you know that, some of you are interested in shells or being here with the museum members, but it's something I always like to describe is that beautiful miracle of shell making that mollusks perform so well. So let's talk a little about shell making. First, I want you to envision a cross section of a bivalve, which you'll see here on the top right-hand corner, such as a quahog. This is actually our southern quahog, and the shell is actually from Sunnyvale. So if you slice that shell, you can see the different shell layers in cross section. And here we are. That's the same species of shell that we have here actually in the museum collection, showing the different layers of the shell. And with the age of the shell being, this is older shell here where the arrow is. And as the animal grows, the shell grows with it. The animal makes more shell. And that's the youngest section of the shell here. Now, the other image here shows this, the shell in cross section in orange there, and parts of the animal that are making the shell. So the message I want to send to you here is that there is a special area in the shell called the extra paleo space, which is right here. And it's just between the shell and the animal, in this epithelium, this part of the animal, the mantle, called the mantle, that is making the shell thicker here. And also another area that where the shell is being made at the mantle edge. So the shell grows in thickness in this bivalve and grows in size at the very end here. So this extra paleo space is sealed from the outside environment. And that's where the formation of that miracle substance, the calcium carbonate, that's where that fusion between calcium and carbonate is happening. So calcium comes from the environment, carbonate comes from the environment, and is transported to the different tissues here and bumped into the extra paleo space for the formation of shells. It is kind of simplified. There is a relatively complex system that involves many enzymes and cool stuff going on. But just to show you more or less what happens and why calcium carbonate is needed and why we're talking about all these things here today. That's another vision again of the same situation, just to reinforce the idea in your minds. That firms up the concept of shell formation, hopefully, and calcium carbonate bind at the end of, again, as I said, a relatively complex sequence of reactions. So the little green dots indicate the location of shell formation, the extra paleo space. That's where, again, that happy marriage of calcium and carbonate is happening. So, again, I want to repeat that image because that's key to the whole thing. If I could just, if my boss Sam Ankerson told me you can only show one slide today, you don't have time for the other 29. That's the one I'll be showing you, where carbon dioxide increases, carry over as a decrease in carbonate, which will damage shell formation. So again, to firm up, in a more acidic ocean, the shell is more likely to dissolve even as it is being built. And in addition to that, other things happen with the animal, such as growth, that need to happen with the animal, such as growth, reproduction, feeding, and all that, may not happen properly because the animal is devoting, animals are devoting unusual amounts of energy to shell making, spending a lot of energy repairing the shell as those processes are not happening the way they should be happening. Now going to more practical examples of this whole theoretical introduction. Back in 2013, Laura Parker, who is a researcher working in New South Wales in Australia, published a paper way back then, 8 years ago, that outlined the state of knowledge of the impacts of ocean acidification on mollusks globally, as recorded in scientific papers. And Laura was actually supposed to come for Mollusks in Peril and couldn't come, but she was one of the members of the scientific advisory committee for the meeting back then in 2016 here at the museum. Well, Laura found that back then in 2013 that there were studies on about 96 species of mollusks, with the vast majority showing negative responses to increases in ocean acidification, to increases in carbon dioxide in the ocean. So the blue bars show the percentage of negatively affected mollusks, the species considered in those papers, for a total of 96 species, as I said, 66 bivalves, 22 gastropods, and 4 cephalopods. So just to explain a little more how this happens here, you have a percentage scale here between 0 and 100. And let's take the example of mussels, where about 70% of the studies show negative effect and 30% not affected or positively affected, most likely not affected rather than positively affected. So let's take a look now at the first group of examples, the ones that I mentioned in the introduction, in my table of contents for the talk. The pelagic of open water mollusks called pteropods. They spend their entire existence in the water. They're pretty small animals, about 1-2 millimeters in some cases. The sea butterfly, Limacina elicina, is one of them, and is one of the best studied open water mollusks for for the relationship with ocean acidification. Sea butterflies are eaten by organisms ranging in size from tiny krill, which are small shrimp-like crustaceans, to baleen whales, the large whales, and are a food source for North Pacific juvenile salmon. The photos here from a study done by scientists from the Pacific Marine Environmental Lab in Seattle, Washington State. They show how a pteropod, sea butterfly shells will dissolve over a 45-day period when placed in seawater with increased acidity. Culminating with sheer destruction for the levels projected into the future for year 2100. So this is a lab study where simulations were done showing the gradual sheer destruction of the shells in the sea butterfly. The same group of people did a study that was published in 2014. And I don't expect you to read all that here, but we have some data on it. It was a study published in 2014, led by Nina Bednarczyk, who was back then at the PMEL lab, the Pacific Marine Environmental Lab in Seattle, and her collaborators there. So they did a combined survey in 2011 of water properties and biological sample along the coast of the Pacific Northwest and into deeper water, showing that large portions of the shelf waters are corrosive, are not good for sea butterflies. A little less so in offshore waters, but a percentage of 53% of individuals studied on shallow water, on the shelf, on the continental shelf, and 24% of offshore individuals of that species had severe dissolution damage happening to them. So, yeah, and as I mentioned in the beginning, there's a large body of scientific work now, and I'm not going to go over a lot of that here, but some key examples that I found that I've been thinking about, where scientists are showing some significant negative effects of ocean acidification, for instance, on larval mollusks, which we'll see next. It's curious and very interesting. I mean, to me, it was very enlightening to learn back at the Mollusks Impero Forum here that a lot of those studies were prompted by stakeholders in commercial shell fisheries or in aquaculture operations, especially in the cold water parts of the US and Canada, the Pacific Northwest, New England, Newfoundland, and such efforts, I mean, the efforts to study and research those problems have received consistent funding from NOAA and some of the funding agencies in the US. So here's a good example of ocean acidification impact on oysters in the Pacific Lab website, the carbon dioxide program. So let's take a look now, moving out of, we talked about open water mollusks, the sea butterflies. Let's take a look at larval mollusks. And one of the key groups of mollusks that have been studied for ocean acidification are oysters. For instance, oysters such as the eastern oyster, Cursor virginica, which we actually have here in Southwest Florida. They have free living larvae that may live in open water for around 2 weeks. At that point, and that's the key point where the shell is not heavily calcified and therefore being very open to fluctuations in acidity in the ocean. So at that point, again, the shell may be strongly affected by ocean acidification in that open water stage. So after the gametes, eggs and sperm are released by the parents, and the egg is fertilized, there will be an open water larva that will last in the water for about 2 weeks. And that larva has a very thin, very delicate shell that's very susceptible to be damaged by a decrease in seawater pH. So that's a picture of actually from our website of a local eastern oyster, and a study done by scientists from, I think, the Virginia Institute of Marine Sciences and Stony Brook University in Long Island, where they've shown that the presence, increasing levels of CO2 are really damaging to the shell at that stage. So what you see here are 4 different concentrations of carbon dioxide, starting with the normal, quote unquote, pre-industrial level of 280 parts per million. The present, actually the present now is 400. Here's the present back then in this study was 380, has increased a little bit. So, and what happens is that all those shells are about the same age. They are larval shells about the same age. And under increased concentration of carbon dioxide, the shell is reduced in size at the same age. Statistically speaking, if this is not done just with one of each, it's done with several of each one, and the average is taken. And the result is that the average for the high concentration of carbon dioxide is that the shell will be smaller. There's also damage done to the hinge where the larval shell cannot open and close properly because the hinge, which is that section of the shell where the one valve is touching the other, where the closing and opening happens, that hinge is damaged by increases in carbon dioxide. Another example by the same group of scientists, the 52-day-old bay scallops. All 4 rows here are scallops of exactly the same age, grown in the lab under different levels of carbon dioxide, a pre-industrial level, and then a very high concentration, showing the damage done in terms of size. So shells under acidic conditions do not grow to full size for that age. And on the right column here, magnification of the outer shell layer, the outside of the shells of those individuals show shell pitting and dissolution. That's not normal. So for reference, again, the current average concentration of carbon dioxide is 400 parts per million. So this is another commercial species in the Pacific, in New England and the Atlantic seaboard of the U.S. An important component, of the economy of shell fisheries in that area. Yet another one, and that's the last one, but showing for larvae for small, young age northern quahog, mercenaria, larvae grown under near pre-industrial carbon dioxide concentrations of 250 parts per million, show faster growth and quicker metamorphosis, as well as higher survival and other qualities, if you will, when compared with individuals grown under modern day 400, 390 levels. And you see here the projections into the distant future, showing that this tends to be species will be, the larvae will be less and less in size, would be smaller in size, and they were malformed and eroded. So just some examples of the potential damage of having a lot of carbon dioxide entering the ocean. The next example is on adult shells, and it's three scientists from the well-known and famous Woods Hole Oceanographic Institution in Cape Cod, Justin Rice, Ann Cohen, and Dan McCorkle. They reared Florida fighting clocks in seawater under different levels of atmospheric carbon dioxide, so they increased the concentration in the air, and to see how the shells were affected by increased ocean acidity. So on the left here, you have a shell grown under normal, on today's levels, 400 ppm, and still has a normal shell with bumpy, knobs and protuberances. The shell on the right, and that's not the only one, it's a series of them that show the same defects, a shell that began to deteriorate, a much thinner shell with the knobs dissolved away, and so on. So that's just one example of the effects on adult shells. And just to to be fair, I want to show an example here of some species that may actually benefit from exposure to acidic waters. And this is a study done by scientists on the west coast of the U.S. Working on the Olympia oysters. Very tasty, by the way, exposed to a combination of elevated temperatures and acidic conditions. And they did that in the lab. They basically worked halfway in the lab and then took the young to the natural environment in different places. So basically, the higher water temperatures that they part of their experiment caused the oysters to spawn earlier, and those effects were canceled out when combined with acidification. And then they transplanted the exposed oysters offspring to 4 estuaries in Puget Sound, there in the Pacific Northwest, and observing that the offspring whose parents were exposed to acidified conditions in the lab had higher survival rates in 2 of the 4 bays they studied. So they took the oyster, we call that stage the SPAT, S-P-A-T, just after they settle down from the free living larval life, and the ones that had a combination of growing in warm water temperatures and then exposed to a little acidification had higher survival rates. But this seems to be the exception rather than the rule. In most cases, the presence of carbon dioxide is not a cool thing. So I want to show you here, and this is getting close to the end. Just want to show you here several projections done by in a compilation of carbon dioxide in the fossil record, in the geological record, prepared by Chris Langdon of my old alma mater, the Rosenstiel School, University of Miami in Key Biscayne, Miami. So when he looked into averages for different rocks in the planet that kept a record of carbon dioxide, and found that the geological records being pretty stable. There's some fluctuation, going back starting around 800,000 years ago, little fluctuation here and there, and then the increases that we see now with the observed global concentration of about 380, 390 parts per million, and then some worst case scenario here of a very high concentration by year 2100 of about 900 parts per million, and a best case scenario, lower emissions at around what is that, 550 parts per million. The whole idea is here is where we want to go as we get closer to the end of my talk, that it's not always that not all hope is lost. I mean, if we can manage to lower the emission of fossil fuels, bring back some of the deforested areas, we may be able, if not reverse that, at least we can alter or bring it to a lower case scenario of lower emissions of carbon dioxide, and with the resulting lessening the rate of input of carbon dioxide into seawater, into our good oceans. So just to give you one idea here of if we try to it's very hard to convert the parts per million of carbon dioxide into a pH, because there are many factors that interplay there, like temperature being the most important of them. But roughly speaking, you can convert about 400 parts per million into a pH of 8.1, 8.2, and if you want to go all the way up to a pH concentration of 1500 parts per million, higher up here in the graph, that pH would be 7.7, and that's not tenable for marine life, especially the ones with calcium carbonate. So I don't want to be all gloom and doom here. We have some closing thoughts, and I want to propose that well, first of all, to again bring the subject, bring the topic that mollusks are very important. They're very important to all of us, even all of us who, people who don't know, because they're a big part of, the planet's food webs, important part of the economy. But there are other animals that are affected, and corals being also extremely important because coral reef systems are the support structures, ecologically speaking, to a whole plethora of marine invertebrates, including mollusks. So as the corals go, things don't look good for everybody else in coral reef systems. So that change that we saw today, some of those examples, this is happening fast, and we really don't know the extent of the impacts that we're seeing and the potential for damage that's involved. That we have to keep that in mind too. And so the effects of ocean acidification may work in tandem with synergistically, when it's 1 + 1 is not just 2, it's more than 2. With the effects combined with the effects of other human-induced alterations to the environment, such as climate change, which is closely associated with ocean acidification. And last but not least, never too late to act and try to reverse, at least in part, the bad effects of the increase in atmospheric CO2 and ocean acidification. I think that's my message, and I want to thank you all for being there today. I'm going to stop sharing my screen and take a look at your potential questions here. I want to thank my my new boss, Sam. Sam was really helpful. I run a like a sneak preview of this talk by him, and he made some very good suggestions, and appreciate that. Appreciate all of you registering today and attending. So let's see. Well, let's see. Well, the first question, you hear me, right? First question comes from Joyce Ross. Does removing shells from the Gulf and oceans change the pH of the water and the calcium available to growing shells? I think that in theory, yes, But when you look at the number of shells that are out there, when a good example that I like to give is the size of the continental shelf, for instance, here in on the west coast of Florida, the left coast. Um, it's so big. There's so much environment underwater for mollusks to grow that just removing the shells from the beaches doesn't cause a detectable effect. So if I had to choose between yes and no to the first question, um, I would say no. No, it doesn't. Um, the problem is not removing the shells. Yes, the shells can be a source of calcium in the long run, but the main problem is the removal of carbonates from the water and the imbalance in the carbon dioxide cycle in the ocean caused by increase in atmospheric CO2. That's what you have to keep in mind. And my good friend Phyllis Sharp is asking, does an acidic ocean actually dissolve the shells or just prevent the animal from creating more shell? I think that, and I, no, I may, this here, that's a tough one, but I would tell you what I think. Um, we saw that the first effect that we see is a decrease in the ability of the animal to make good shell. It keeps doing making shell, but the shell is being made at a much slower rate with imperfections, with slowing down, and most of all, um, with the animal using energy to achieve that ideal shell that could be used for something else. So it's not only not being able to make the shell the way it should be, but the fact that the energy is being wasted. It's the enemy. It's like imagine you're used to walking on a street or jogging on a sea level, jogging in Florida. I mean, and then all of a sudden you go to the Andes and you have to run uphill. That's what the mollusk is doing under ocean acidification. Is that shell making is like you're trying to climb 1,000 feet in a very short distance. Uh, yes, it will you go up there, but a lot of stuff is not going to happen because you're devoting all that energy to shell making. Now that doesn't mean that the shell doesn't pit. I think I've shown an example here where the larval shell is actually first of all, the sea butterflies get directly affected. The thing will really damage the shell directly. Just interaction just between the acidic water and the shell surface. And when you looked at some of the, I don't know if I can go back here. I probably shouldn't, but what I want to say is that there is a slide there where I show the surface. I think it was the quahog, larval quahog, the edible Venus clam, where the surface of the larval shells was being pitted after being formed by the acidic water. And that's because that process is sequestering, I think, some of the carbonate out of the shell. Maybe I think that's what's happening. So the answer to Phyllis' question is, I think both, and more. It's the lower acidification will hamper prevent the animal from creating good shell, and the more intense, the stronger acidification will actually dissolve the shells, and that's what we don't want to see. I don't see any more questions. So. If not, I want to thank you very much. This recording will be available in our website as soon as we go over a couple of hurdles there with YouTube. And I want to invite you again to Cynthia Barnett. I know Cynthia is there in the audience, who is a fantastic speaker, a super researcher and journalist. And you'll really enjoy her program on April 22nd, which is, I think, Earth Day, by the way, right? Anyway, thank you all, and avoid that acid. Thanks. You like it? Thank you. Thank you.
Well, good questions.
Yes.
So Phyllis's question was really good.
Yeah, and Phyllis. Yeah, and just between you and I and Becca when we was there, I was really nervous.
Oh yeah.
No, if you don't get nervous, I mean, if I don't get a little nervous,
Okay, I guess that's good. I mean, you've done a lot of talks, right? But
yeah, but
yeah.
it's always.
Do you find Zoom or in person is
I
more
prefer
more?
to do it in person.
You prefer in person?
I don't know
Okay.
why. I think that there's you cannot gauge the audience when you're doing that, and you know, I've been doing this for so long that in public that I can't engage people. Okay, and I cannot do much of that. But I hope it was the message was
good.
good. It's not an easy topic, but
And you know, we had I think we had 50 people consistently all the way through.
oh really?
Yeah. That's what I counted.
Okay, great. I haven't didn't count. At some point I saw only 28. So,
No, that must have been the very beginning.
yeah, I think it was.
Yeah,
Well,
no,
thank you
we had 50.
It was a very nice introduction. Thank you.
We had 50 sort of, you know, soon after you started talking, and then 50 at the end.
Okay. Well, thank you, and
Sure.
I'll see you tomorrow.
I will see you tomorrow.
Busy day tomorrow, so.
Yeah.
I'll be here at.
The cleaners are coming. You
I'll
remember
be
that?
here 6:30.
That's a long day for you.
Oh, that's okay. You know, the alternative is not good. So, yeah, thank you.
Do you don't have a key to the store by any chance, do you? Or no?
I think they keep to the story. Oh, pop-up.
No, not the
Oh,
pop.
the regular one.
You sure the master gets in there?
Oh, by the way, I had yesterday, I sent an email to Patricia, and she's made all this, including the badge,
Oh, okay.
because it's protocol, and then we'll send her a letter. I'll show it to you. I don't think I have that letter. I think Laura had the letter, but it's kind of a
Determination on that.
it's a send here in person.
Yeah. So I'd like to just write her a little note saying thank you.
Yeah. Well, she did a tremendous job. It's very, very professional. And
I won't mention anything. I won't admit to anything.
I'm sorry.
I won't admit to anything about Lowell. I just want to say thank you.
Yeah, I know. Yeah, I was afraid for a moment there that she would, do something so bad. But she was very, man, you know, we made, you know, except for this boat situation, I mean, her life here was really good. You know, the sense of, valued a lot. Every day I went to her and say, hey, you know, this set of images just from us. It's always, so she felt good about that.
So I want to talk to you again about this. I want to, I'd like to, you know, as I said in the meeting, I think I said, I want to keep doing exhibitions at least down there, and sort of have some ideas, which I want to talk more with you about at some point. You know, like we're gonna need someone to give us some money to, be able to have it. But I, in order to get something up, after this show comes down, what I can think of, that we can do that would be cheap that's here is some sort of nice thought. I was, you know what I was even thinking? It could even be like, since it's 25th anniversary, it could be like a shell that we blah, because like the labels are written, and we have these pictures, and we could sort of take a look at it where we're looking for, yes, interesting ones, but also just like really wild, really beautiful ones, or like,
All three.
and just, that might be a nice, because then people, it would draw attention to cataloging the project.
Yeah.
It could draw attention to,
And
I think it could be attractive to a sponsor, like the shell wing thing we were talking about before, and it gives people more shells. Like downstairs we're great. We got the animals, that whole experience, and then
I want to do something from that. Well, you have two sources. I mean, I'd love for you to be able to choose some. And there are two places you can go, and I'll show you tomorrow because at some point, one is the blog. The blog goes back. It has a lot of cool information because I'd love to do that. The other one is when you go to our website, it's hidden there, but it's like search the collection. And there's a little dance you do there, like 3 steps, 3 clicks, that brings all the images, like 3,000 that they've done so far. And the images, when I say 3,000, each one has like 5 or 7 components that are composite into one entity, something. Once she's done and James can do. I need to hear about it. And look at some of the translucent, you can see the thing.
Yeah, and for a lot of it too, it shows that people never see because they're so small.
And then when you look at the picture, because we use this fantastic technology there, you don't even need to tell. Actually, you should, but if you know, you have something about this big that's like 1 millimeter long, and it's beautiful. So, yeah, I think that would be great, and I'm all for it. And I'll work long hours to make it happen.
Yeah, it could be fun.
And all we need to do is to find a way. You agree with printing then, right?
Yeah, yeah, we would have to, I mean, depending on the amount of money available to us. Yeah, and I need to ask around maybe to, some of my former colleagues and stuff like that. I mean, there's the expensive version, which is to get nice prints made and put them all in frames. And then there's other versions, to do that, for sort of turning stuff into wallpaper, or we're like, thinking about, sort of a color Xerox, not really a color Xerox approach, but like a color printing kind of, approach, and like maybe not everything is sort of framed as if it's a work of art. I don't know.
Well, we can do it, depending on the size. We can do up to 1117 here. And that's, in your opinion, I think you're being small.
Yeah.
But if that's the size that's acceptable, we can do it here using a high quality version with color printing.
Yeah.
Or just take it to Kinko's and
Yeah.
you can do like, I can do it quick and dirty. The thing is, the cool thing with them is that they're high resolution. I mean, some of those original files, and I have them all. I have, because of the protocol, we see the original composite. Some of them are 350 megabytes. So you can make a outdoor sign with them, and it will be sharp. So the sharpness is really. So that would be cool.
Okay, maybe think about that for like summer show, and then that'll give us a little bit of time to think about.
It would be cool to also
Next
do
season.
another Mollusks Pteropods.
What's that?
Another Mollusks Pteropods would be great, either live or.
Oh, symposium. Yeah.
Yeah, and I have a funder I have to talk to you about that. I haven't funded the first one. He came to me a couple of months ago and said, hey, if you want to do a second one, let me know. He paid us $25K to bring people in on paper hotel. And if we do it Zoom, we don't have to lose that much money.
See local. Yeah.
Anyway, thank you for being part of it.
Okay, so you're sure the master key? Because I tried the master key down there before and I couldn't get in, but maybe I was just.
I mean, you're talking about the double doors that.
Yeah. It should
Where
work.
we go now?